Hello, students. Welcome to the 35th lecture on particle physics. And today we are going to talk about neutrino detection. And what I had told you that neutrinos are the most abundant particles after photons, but they are least understood. This is because the probability of interaction of neutrinos with matter that is very small in comparison to the photons or in comparison to a proton interacting with another proton, that is this through a strong interaction, or a pion interacting with a proton target through a strong interaction. The strong interaction cross section in general is of the order of 10 power minus 24 centimeter square or 10 power minus 26 centimeter square, while electromagnetic interaction cross section is of the order of 10 power minus 30 centimeter square or 10 power minus 32 centimeter square, while weak interaction cross section is of the order of 10 power minus 40 centimeter square, and therefore it's really small. Now today we are going to first understand what does it mean 10 power minus 40 centimeter square or 10 power minus 32 centimeter square. How in the layman's language we should understand cross section. Now this topic is important here because when we are talking about gigantic detectors having 40 kiloton of iron materials, for example, that is planned at India-based Neutrino Observatory, or many kilotons target at Dune or at Super Kamiokande. Therefore, the important point is why we need such gigantic detectors. The simple answer to that is to have significant number of events. As you can recall, the Ray Davis experiment that went for almost 25 years to have significant number of events, to make a statement which should carry some weight about the solar neutrino discrepancy or anomaly. And then when we arrived in the 21st century, when the science and technology was moving at very rapid pace, we had engineering and all that, people started to think of these huge detectors having good electronics and all that. Now we are going to just talk about first what is the cross section. But before that, why we are doing this topic? The simple answer to that is once neutrinos are produced, it is very difficult to detect them as these are weakly interacting particles. These particles almost never interact with other matter. We need gigantic detectors to detect them. Or if I ask you that why we need such detectors, the simple answer is that though we have abundance of neutrinos even from the relic, but we have not yet detected them. We have detected cosmic microwave background radiation almost half a century ago, but we have not yet detected relic neutrinos. This is because these are low energy neutrinos and we need bolometric kind of detectors, very low energy detectors to detect these particles. And in simple terms, what we can say that suppose we are talking about interaction of photon with a target particle and we are saying that interaction is happening. Then if we want to have such interaction with neutrinos, then what we need, instead of a single particle, here we would need 100 million particles. Therefore, you can understand by looking at these two comparisons that if I am saying that I had sufficient material to have single interaction of photon with a target particle, then the question is how much more I would need to have a single interaction with a neutrino particle. And the answer to that is you would need 100 million more particles in that area to have a single interaction. And that is why these experiments are really difficult. They need both large amount of target material, they need a large span of time to have the sufficient number of events, etc. Therefore, what we are going to first talk about is the cross section. What do we understand by the term cross section? Now, in simple term, cross section is probability of interaction, or it is the area over which A plus B interacts to give you 1 plus 2 or 3 plus 4 plus 5 plus 6. These are all particles, different particles. For example, if I am saying that I am talking about pion plus proton, we can have elastic scattering. We can have pi 0 plus n inelastic scattering. We can have other processes. Therefore, the important point is that cross section tells you the probability of interaction. And in simple terms, if I say that we have the strong interaction cross section to be 10 power minus 24 centimeter square, the electromagnetic interaction cross section to be 10 power minus 30 centimeter square, say, and weak interaction cross section is 10 power minus 40 centimeter square. In simple terms, what does that mean? This means that suppose I have a beam of particles and say the flux that we are talking about is n number of particles crossing unit area per unit time. Therefore, this is what we in physics we define flux, number of particles passing through unit area per unit time. Now we have a target, and if we want, suppose we have single pion coming per unit area per unit time, and then we want to have an event. This is the constraint which we are putting, that no, give me one event per second. Then how much target material in 1 centimeter square we have to put before this pion? The answer to that is we will have to put 10 to the power 24 particles in 1 centimeter square to have one interaction. Now, if somebody asks me that what will happen when instead of this pion we will talk about neutrinos, then we will say that now, since the neutrino interaction cross section is very small, you need, instead of 10 power 24 particles per unit area, you need 10 power 40 particles per unit area. And this, you can understand that what this 10 power 40 means. And you can take another example. If I say that there are 1000 particles coming per unit area per unit time, instead of 1, now we are talking about 1000, then here you need, instead of 24, 10 power 21 particles to have single event, and here for neutrinos, if it is true, we need 10 power 37 target particles per unit area. So therefore, the important point is, if you want to understand cross section, the important point is that if I take a loaf of bread as a detector, and then we are bombarding particles on this detector, say this is a detector, loaf of bread, and then you have divided into many slices, and say in this detector you have filled water. Now the density of water is 3000 kilogram per meter cube. Density of iron is 7000 kilogram per meter cube. Density of lead target is 12,000 kilogram per meter cube. Therefore, what I am telling you, that density of water is 1000 kilogram per meter cube. Density of iron, this is water, this is iron, 7000 kilogram per meter cube. Then you have lead, 12,000 kilogram per meter cube. That means, in simple terms, in a meter cube or in a centimeter cube, if you have lead, then that means you have more number of particles through which a neutrino will interact. If you have water, then you have lesser number of particles in a 1 centimeter cube or 1 meter cube through which the neutrino will interact. And then if I say that I am dividing into, say, this total length is L, I am dividing into a small differential element dx, and density of this material inside this detector is rho. That means in dx length, how much interaction target we have, that will be rho dx. Now if particles are getting incident on this and you have a target material before it, then if there will be interaction, the particle will move away from the straight or from the forward direction. And therefore, if I say that dn is the change in intensity of the beam, then this dn will be proportional to the number of incident particles, because as we have from 1 we have gone to 1000, we have seen that the probability of interaction increases. For example, if I have got a room of 1 cubic meter size and there are balloons filled inside that or small balls inside that, and I am throwing another, say, red ball, and I want to hit one of the balls which are there in the room, then that means 10 power minus 40 means, in simple terms, that I will have to try 10, how many times, that will depend upon in 1 centimeter square how many balls are there. And if I have got a ball of 1 centimeter square size and it is coming per unit area per unit time, then if it is in unit area, if we have one target particle and one projectile, then I will have to try it either 10 power 40 times to have one event, or I have to wait for 10 power 40 seconds. You see, the Davis experiment waited for 25 years because he had no control on the solar neutrinos. They were getting produced inside the core of the sun. He could not increase in any way could not increase the flux of the neutrinos, and then the detector was also fixed. Therefore, at that time, because of the limited technologies, the size was limited. Therefore, the detector size was limited, and you cannot play with natural sources of neutrinos. Therefore, he waited for 25 years or 5 years or 10 years, something like that. And simply why it's happening? Because when you are talking about event, that is a convolution of the number of incident particles that you are talking about, That is a convolution of the interaction cross section of the projectile with the target. If the interaction is through a strong interaction, the probability of, or the chances of interaction is more. If the interaction is through weak interaction, the chances of interaction gets reduced by a huge amount, and therefore you have to try many times. Therefore, in simple layman language, what I am telling you, that I have got a 1 cubic centimeter detector, and there is only one particle per centimeter square, and in the projectile that have is also falling one particle per centimeter square per second, then I have to either try it in about 40 times, or I have to keep on trying and wait for 10 about 40 seconds to have one event. Only there will be one time it is going to interact. And if you can recall from my lecture, what I had told you, though trillions of neutrinos are crossing through our body per second, but in a lifetime of 80 years, typical human lifetime, the chances are one is going to interact with the matter which is contained in our body. And that is why we try to go for gigantic targets. Therefore, the thing which I am talking about, that when you have you have divided these detector into various slices of thickness dx, and then in this you are talking about, when you have taken a slice, you are talking about the amount of atom that is there in that slice is proportional to rho dx, then the number of particles that will be reduced, because here you are talking about those number of particles which have not scattered, they have gone in the straightforward direction. Now the number, that means if you can say that this is some number nf, this is some number ni, then this is basically I am talking about nf minus ni. So therefore this nf minus ni, final minus initial, for this length, okay, that I am calling it by name dn. This change will be proportional to the number of incident particles, and this will also be proportional to rho dx, where rho is the density of the target material. As I am telling you that if you have water, the density is quite less than what you have in the case of lead target. And then if you remove this proportionality sign, and look at dn, what is dn? Number of final particles which has not scattered minus the number of initial particles. As we can directly say that always number of final particles which have not scattered will be less than the number of incident particles. It will be the only case when there will be nothing inside that detector. You will have a vacuum, only then nf will be equal to ni in general, in principle. Therefore, dn will we replace it by a proportionality constant with a negative sign. This is coming because dn is nf minus ni, and this proportionality constant is known as the cross section of a reaction. And if you notice, this is number of particles. This is a number of particles coming per unit area per unit time. Number of particles coming per unit area per unit time. What is this? This is the density of the particles. This is the number of particles that will be contained in some volume, because we are talking about density. Therefore, this is number of particles per centimeter cube times the length. This length means I am talking about centimeter. Therefore, what we have, we have n, the number of particles crossing per unit area per unit time. We have rho dx, number of, this is the number density, the number upon centimeter cube, and this is the length. And you see on this we have the number. Therefore, the important point is that dn is the number, and here we are talking about number of particles crossing per unit area per unit time, and rho is the density, these many particles per centimeter cube, and dx is our length. Therefore, the important point is that here we have a number, or we can write this as dn upon n. This is equal to minus sigma rho dx. And then if we integrate it from, say, the initial point of the loaf of bread x is equal to 0 to the final point of the loaf of bread, the length of the bread is L, then this will be Ni to Nf dn upon n, and this will be equal to minus sigma rho dx. And as you can notice that if we integrate this we are going to get log nf upon ni. This is equal to minus sigma rho times L, and that means nf is equal to ni e to the power minus sigma rho times L. Now you see, this guy exponential should be a dimensionless quantity, and therefore the dimension of this fellow, this should be centimeter square, and that is why we say that the dimension of sigma, the cross section, is that of dimension of area, because this is per centimeter cube, this is centimeter. Then to make this dimensionless we need centimeter square, and therefore this nf is the number of final particles which have got unscattered at a length L. This is the number of incident particle at x equal to 0. This is equal to minus sigma rho L. And if you can notice that when I will make this L to be infinite, then number of particles, those will be unscattered, will become 0. Therefore, when x is infinite, then that means all of them have got scattered. All the incident particles have got scattered if the detector is of infinite length. And in other words, that means by increasing the size of the detector through which these particles are going, the probability of interaction is going to increase. Now, let us stop here, and from this point, we shall start our discussion in the next lecture. Thank you very much.